Hi, my name is Claire Terhune, and I'm here to give you a brief intro to the MicroCT Imaging Consortium for Research and Outreach, or MICRO for short, at the University of Arkansas. This facility is funded by the National Science Foundation and supported by the Center for Advanced Spatial Technologies at the University of Arkansas and the Oklahoma State University Center for Health Sciences. I'm also going to provide a brief overview of how CT imaging works and some of the equipment specifications we have here at MICRO. First of all, why should you be interested in MicroCT? MicroCT is shorthand for microcomputed tomography. Just like when you go to the doctor for a medical CT scan, MicroCT scanning uses X-rays to peer inside objects. This technique is non-destructive and generates 2- and 3-dimensional images of objects based on their density. These attributes make this technique widely applicable in many fields, including biology, paleontology, medicine, archaeology, manufacturing, engineering, and many more. There are many benefits of MicroCT imaging. This technique is especially powerful for examining the internal structure of objects, but also useful for generating 3D models and 3D prints of objects, particularly those that are rare or one of a kind. This is especially valuable for minimizing the handling of fragile items, and MicroCT imaging easily allows data archiving and sharing via a wide variety of platforms. So how does MicroCT work? The goal of all CT imaging is to create volumetric renderings of a 3D object. This means that a series of 2D X-ray projections are algorithmically combined to create a stack of cross-sectional slices that, when combined together, provide a 3D image of the internal and external structure of an object. These 3D images are made up of many cubic volume elements called voxels. The smaller the voxel size, the better the resolution of the scan is, and the more easily smaller structures can be detected. Two basic structures are common to all X-ray and CT imaging equipment: the X-ray source and the detector. The object, sample, or individual of interest is placed between these two structures, and as X-rays are produced, differences in the density of the materials being imaged attenuate or stop some X-rays from fully passing through the object. Those X-rays that remain are picked up by the detector. That detector essentially acts as digital X-ray film. The more dense the material, the more likely it is to stop some or all of the X-rays passing through it. This technique comes in all shapes and sizes. Most people will be familiar with clinical CT scanning, where an individual lays on a gantry and the X-ray source and detector rotate around the person or anatomical region being investigated. Clinical CT imaging usually has a resolution of around 1,000 microns or about 1 millimeter. In contrast, MicroCT imaging can produce datasets with resolutions between 1 to about 100 microns. Much of this resolution depends on the size of the object being scanned and the equipment in use. MicroCT systems can be small and tabletop, medium to large cabinet-sized systems, or can be walk-in systems. Each of these different setups has its strengths and weaknesses. The MicroCT equipment we have at the University of Arkansas Micro Facility gives us considerable flexibility in the size and density of objects that can be scanned. The specific system at the heart of Micro is a Nikon XTH225ST, which is a large cabinet-sized system. There are a variety of imaging parameters that can be adjusted to optimize CT scanning. These include the beam energy, beam current, power, which is a product of the energy and current, as well as options such as exposure length, analog and digital gain, the number of frames that are averaged to produce an image, and the total number of individual projections or X-ray images that are used to produce the volume rendering. Our system has 3 interchangeable X-ray sources, or targets. A nanoscale transmission target that is particularly suitable for small and less dense objects, an ultra-focused reflection target, which is great for microscale imaging of medium-sized and medium-density objects, and a rotating target that also produces microscale resolution images, but is more suitable for particularly dense materials. The flat panel detector present on the Micro equipment is a Perkin-Elmer. The 16-bit detector has 2000 by 2000 active pixels and a maximum frame rate of 3.75 frames per second. These specs allow for a total of 65,000 plus grayscale values. The detector is also motorized, which allows it to be positioned closer to the X-ray source to further optimize scanning. Lastly, the sample manipulator moves in 5 axes and has a wide range of possible travel within the cabinet. It can support objects up to 50 kilograms in weight. Positioning of the sample using the manipulator is important and largely related to the size of the object. Voxel size of the scan is inversely proportional to the object size and position relative to the X-ray source. What about MicroCT safety? As with all X-rays, as well as many environmental sources, MicroCT scanning produces radiation. However, the vast majority of the radiation produced by the MicroCT remains inside the equipment due to the full radiation shielding that is in place. Radiation measurements on the exterior of the machine are less than 0.1 millirem per hour. This dose is considerably lower than many doses typically experienced by the average US resident, including things like from a chest X-ray or from cosmic radiation. Following CT acquisition, the raw images or projections must be processed to reconstruct the data. This is typically done in software linked to the equipment, in our case CT Pro 3D from Nikon. This software algorithmically locates the center of rotation from the object and then reconstructs the data into a 3D volume. The reconstruction software can also help correct some imaging artifacts, or it may be the first time that imaging artifacts are identified. Common types of image artifacts in MicroCT include things like cone beam artifacts, which are caused by X-rays glancing off of denser materials, resulting in a streak or shadow effect. Streak or extinction artifacts, where denser materials may cast a shadow behind them, where X-rays were not able to penetrate the material. Beam hardening artifacts, which occur when lower energy X-rays produced by the X-ray beam are absorbed when passing through the object being scanned. This causes the appearance of a more dense shell of the object, when in fact this is not the case. Ring artifacts, which are visualized as concentric rings around the axis of rotation of the object. These tend to be more common in more homogeneous materials. And lastly, motion artifacts, where the object may have moved during scanning, often causing a failure in the ability for the reconstruction software to find the center of axis of rotation of the object. Once finalized, the data can be exported in several different formats, the most common of which are DICOM and TIFF stacks. Both of these data types have corresponding metadata, which typically describes the voxel size and other scan parameters. The primary difference is that DICOM datasets encode the metadata within them, where TIFF stacks do not, and therefore parameters like voxel size must be manually adjusted in subsequent analyses. Last but not least, the data must be analyzed. There are a variety of programs, some free, some not, that can be used to further process and analyze MicroCT data. Some of these programs are listed here. We hope this has been a helpful introduction to MicroCT and to the equipment at Micro. Should you have any questions about MicroCT scanning or would like to inquire about options for undertaking scanning at Micro, please feel free to reach out to us via email at micro@uark.edu, visit our website at micro.uark.edu, or find us on social media. Happy scanning!